Newton's law for universal gravitation. The truth is, Newton had his hand in everything. It's kind of amazing that this law actually works out. And I don't want to get into too much of the weeds about it because I hate to say it like this. I don't think you'll appreciate it. But there was no way for Newton to measure this. He kind of reverse engineered this rule. And it's hard to explain why, but understanding that gravity is a force of attraction, that part's not so terrible. And I think that a lot of you have no difficulty with that idea because you feel like you're being attracted to the earth. But for Newton, this was a revolutionary idea. He had no way of framing this because no one else had thought of it this way before. And to be quite honest with you, there's several different laws in the universe that appear to have the same form as Newton's law of universal gravitation. And I don't know why, but I have a feeling that it has to do with the way spheres are related and the way the effects of the field of the effect and shape of the gravitational field, I feel is probably why this law looks the way it does. But I have no way of explaining to you why it exists the way it does. It involves three properties: the masses of the two objects, their separation distance, and a constant of proportionality. Newton's law of universal gravitation states this, that the force of attraction between any two objects with mass is proportional to their masses multiplied together, divided by the separation distance squared. This is known as an inverse square law. And there are dozens of them in physics and chemistry. The electric force, the thing that holds atoms together, also obeys an inverse square law. It shows up a lot in physics. And again, I think the reason has to do with the shape of the fields. But the truth is, I'm not sure where or how Newton came up with this. The first thing I want to point out is that these are all predicated by a constant of proportionality, this value of G. This is not 9.8. Notice it's a capital G. That's on purpose, and it's on your equation sheet. Find it, please. It's a universal gravitational constant. And it is a tiny number, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Did you guys find it? Now, my experience with students and dealing with this inverse square law is not good. So we're going to do some practice here, but I want you to understand the basics. First, this tells you the size of the force, the magnitude. But please note that this force actually acts on both objects due to Newton's third law. It is the force of attraction between both objects. There's a vector component to this force, and the way that's actually written out is a little bit complicated and cumbersome. So we're not going to do it. We're going to skip that part. You have to assume that there is a line that can connect both objects, and the force lies along that line. It's pretty straightforward. So M1 is attracted to M2, so the arrow points towards M2. And M2 is attracted to M1, so that arrow points towards M1. So the direction of the force is along the line that connects the two objects. But the size of that force is given by this relationship. Now, you don't have to understand where this relationship comes from, but there are some things that I think are important, and I'm trying to give you what I think you need to know. These would be bullet points on a PowerPoint, but you know I hate PowerPoints. So bullet point number 1, this only can tell you the force between two objects. If there's a third object, then you have to find the force between all the pairs of objects. This equation can only be used to find the force between any two of them. So again, you introduce a third object, m3, suddenly you have to use this equation 3 times because there are 3 pairs. Right? There's this pair, and that pair. So Newton's law of universal gravitation becomes very complex the moment you have more than 2 objects. In fact, we will never deal with anything more than the 2-body problem. The 3-body problem is very complicated. But we will deal with the 2-body problem, the force of attraction between any 2 objects. The second bullet point, this force is tiny. It's really small. But it's between all objects with mass. So you and the table, you and the person across the classroom, your water bottle and the floor, they're all being attracted together. But remember, all of them are scaled by this universal gravitational constant that is 10 to the negative 11th. To put this in perspective, let's consider the force of attraction between any 2 of you in the classroom. Let's say that the 2 people we're talking about each have a mass of 60 kilograms. And let's say you're talking about somebody across the classroom who is 5 meters away. Using your calculator, find the force of attraction between these 2 people. This is also where I figure out if you guys can use your calculator correctly. Did we talk about how to deal with scientific notation the other day? If we didn't, I'm about to find out whether you can or not. 1 times 10 to the negative 8th. If you have more registers, you might get 9 point something times 10 to the negative 9th. Now, for the rest of class, I will write everything with the E in it like this and not the times 10 to the. Okay. Final answers, put the times 10 to the. But in mid steps, the E is faster and less cumbersome and shows you what should be in your calculator. Now look, a lot of you got different answers. Trust me, that's what I'm prepared for. First period kind of freaked me out because they all got the right answer the first time. And then they couldn't do anything after that, but they got the right answer the first time. So they did better than you on this first one. But you understand, how do you know? Right? That number's bizarre. And it's very difficult for you to know just by looking at it whether it's right or wrong. That's part of the problem with this, is that a lot of times you're going to get an answer to which you have no idea whether you're right or wrong. And often, what are you going to do when that happens? And trust me when I say multiple choice. This is where you're going to see this, right? It's probably not going to be on FRQs. Multiple choice, where one of the answer choices is going to be something that I know you're doing wrong. Like forgetting to square the denominator, pretty common. Or not knowing how to do your scientific notation correctly, pretty common. Those produce specific answers that are the same every time, and the test writers know that. So part of this is about using the formula, but part of it is about understanding that you might not have any frame of reference for what your answer looks like. Consider this one. Back here a minute. G is in newtons, meter squared per kilogram squared. That may not have been anything you paid attention to, but if you look at what this function looks like, it has to end up in newtons. This part is kilograms squared, and this part is meters squared. G has to cancel those out and leave you with newtons. So that's why the units are newtons, meter squared per kilogram squared. That means this value of G can only be used if you have your value for mass in kilograms and your value for separation distance in meters. Yes, sir. I can't hear you. Then it's wrong. No, it's not wrong. It's not wrong at all. Can you see why it's not wrong? All right. It's good that you should bring this up, but let's explore why the equation sheet's not wrong, and we'll look at it right here. A newton is a kilogram meter per second squared. Right? So they've taken the Newton part and broken up into its base unit, which makes the top meters cubed. One of these cancels out, and that leaves us kilograms second squared here. I would continue to use this if I were you. I'm sorry, meters cubed. I would continue to use this. It will be easier for you because it'll give you a better understanding of the units that you need to be left in. But that's what you get when you break it all out to its base units. The Earth has a mass of 5.97 times 10 to the 24th kilograms. The Moon, 6.87 times 10 to the 21st kilograms. And they're separated by a distance of 7.37 times 10 to the 9th meters. And the Earth has a radius of 6.37 times 10 to the 6th meters. And the mass of the Sun, 1.99 times 10 to the 30th kilograms. And the mass of a proton, 1.67 times 10 to the negative 27th kilograms there. Now, I gave you a bunch of stuff, some you need and some you don't need. But I would like you to find the force of gravity on the Moon. The information you need is present, and information you don't need is also present. Your job is to find the force of gravity between the Earth and the Moon. So, after walking around the room and helping a few people out, you understand it's hard because you just look at the person next to you, you have no idea of the framing of the answer. And although many of you have the right answer, few of you don't, and you have no idea why, and you're off by weird amounts. The correct answer should be that the force is 1.86 times 10 to the 17th newtons. And of course, that's the other thing too. This is a force, so the answer's in newtons. That value for G is got some weird units going on, and that's on purpose. So let's we're gonna practice one more time. And this one is to try and demonstrate something else. So I'd like you to find out the force of gravity on you due to the Earth. To help you with that, there are 2.2 pounds per kilogram. So if you know what your weight is in pounds and divide by 2.2, that'll give you your mass in kilograms. So can everybody just take a moment and use Newton's law of universal gravitation to find the force of attraction between you and the Earth? Most of you are going to get different numbers, unless you're the same mass as somebody around you. This is going to lead to something else in a minute, so give it a shot, please. Point that out again. The R here is the separation distance between you and the object. Although you're standing on the Earth, that doesn't mean your separation distance is 0. It's from the center of the object to the center of you. 0 wouldn't have worked anyways. But I'm trying to wait to see that most people have stopped the pushing of the buttons. But there's something more happening here. I want you to think about changing this just a little bit so that we're dealing with maybe you being dropped near the surface of the Earth. If that were the case, then the net force on you would be equal to ma. Now, if we go one step further here, this is the mass of you times the acceleration you experience. Now, we did mass of the planet, mass of you times g, all divided by your separation distance squared, which was the radius of the planet squared. This equaled the mass of you times a. Now I'm going to spell this out because I don't think everybody's getting what I'm saying. You're just, Monday morning on autopilot, just looking at those eyes. That's what it looks like. But there's an my in both of these, which means this a is the acceleration of gravity near the surface of a planet. Now, if you plug in all the stuff for Earth, you should get 9.8. Whatever number you have right now, if you divide out by your mass, you should get 9.8. Because everybody used the same mass of the planet and the same radius of the planet. So everybody should have the same number here. If yours doesn't come out to be 9.8, you screwed up. Because I guarantee you put these numbers in there, you get 9.8. But this also tells you how to find the acceleration of gravity on any planet or any moon. So that's your next job. I want you to tell me the acceleration of gravity on the moon. And this time, please understand, I didn't give you the information that you need. I'm looking to see if you're resilient enough to find out what you need and get it into proper units. And by the way, this is not the mass of the moon. I was lying to you. You need to figure out how to find these values. Luckily, you have access to an incredible wealth of knowledge. This is about making sure you get your numbers in the right units. I want the acceleration of gravity near the surface of the moon. I'm showing you how to get it right here. I have great sadness. If you looked it all up, you know that you need several pieces of information here. So did you look up the radius of the moon? 1.7 times 10 to the 6th meters. 1,700,000 and something thousand meters. And its mass, 7.34 times 10 to the 22nd kilograms. And even with all of that, you still have to understand that the acceleration of gravity on the moon will be the mass of the moon times g over the radius of the moon squared. Don't forget the squared. And I'll be honest, even getting all of those things together doesn't guarantee you'll get the answer right. Still seeing people not be able to do their scientific notation correctly. Acceleration of gravity on the moon is about 1/6 of the Earth. Now, you're going to have to kind of nail these kinds of things, folks. This is just plug in and chug it in your calculator. But you understand, if they're going to do plug and chug problems, they want to use these. So in multiple choice, you got 1.5 minutes. So just trying to help you see the nature of what the expectation is. I'm not going to spend much more time on this. We're going to do some more orbit stuff tomorrow that's going to require this. You should, if you're having difficulty here, practice. Look, there's a style of question that's going to come up. And my experience last year is that students were challenged by it. My experience this year has been mixed. I want to see if you can do this kind of problem. I don't know whether you have the skill set or not. This problem sounds like this. Two objects, M1 and M2, are separated by distance r. they experience a mutual force of attraction of 20 newtons. Two objects, mass m1 and m2, separated by a separation distance r, experience a mutual force of attraction of 20 newtons. What force will they experience if the separation distance is doubled? Again, the question, what force from gravity will they experience when the separation distance is doubled? My question for you is, do you have a method to solve this kind of problem? Try. Some of you have a method and some of you don't. I want to know who does. By the way, we've seen this problem before. The last time you saw this problem, it sounded like this. An object falls a distance x over time t. If you double how long it falls for, what does that do to the value of x? It's the same kind of problem. These are ratio problems. Some of you know how to do them, some of you don't. Some of you have a method, some of you don't. Raise your hand if you have a method. That's one of you. I'm going to give you a method. There are other methods. I'm going to give you one. If you don't have a method, you should write this method down. First, you have to know what function they're trying to indicate here. We have lots of functions, right? Lots of equations on the equation sheet. They're trying to narrow it down. You need to know what function they're talking about. That's step one. What function are they asking about? I'm not going to write the steps down. You should. So this one, we know. They're asking specifically about this function. Step two, plug in the number that's given. They're going to give you a number. Use it. So step two, plug in a number that's given. I've identified the equation. They gave me the 20 newtons. Step three is not necessary in this example, but could be later. But step three would be to get the number by itself. Step three would be to get the number by itself. We don't need to do it in this case. We have the number by itself. Now, step four is tough. In step four, you should have something that has all variables on one side and a number on the other. Using the variables, plug in the variable that changed. M1 didn't change. M2 didn't change. G didn't change. Separation distance, it doubled. It changed. So step four, plug in the variables and make sure you put in the one that changed. Step five, get all the letters on the right and all the numbers on the left. So I'm going to look at this, and I'm going to move all the letter parts to the right side and all the number parts to the left side. So this is M1, M2, G over 2 squared and R squared. I'm going to collect all of the letter parts to the right and all the number parts to the left. So, step five, get all the letters to the right and all the numbers to the left. You should see your original group of letters there. I see my original group of letters. Plug in the number. So the answer is 5 newtons. There's other ways to do this. You can do it in the form of a ratio. I used to do it with like what I used to call a skeleton equation. I know a couple different methods. I like this one because it solves almost any version of this kind of problem. Even ones where they ask for things that are unusual. It usually works. Now, let's test this, okay? We're gonna try a different question. See if you can do it. I have two objects, M1 and M2, separated by a distance R. Experiencing a mutual force of attraction of 10 newtons. Both masses are doubled, but the separation distance is cut in half. What's the new force of attraction? Again, both masses are doubled. But the separation distance is cut in half. What's the new force? All right, now, I don't know what you guys got, but the right answer is 160 newtons. 2m1, 2m2, g over 1/2 r squared. When I move the letters to the right, m1, m2, g over r squared, to the left I get 2 times 2 over 1/2 squared. This is all 10 newtons. This is 16. So 160 newtons.